Hi, it's time for another math easy solution. Time to discuss further into approximate integration and now look at the trapezoidal rule, error-bound, and go over its proof. Basically, to recap on the formula of the error-bound estimate, which I went over in my last video for the trapezoidal rule for approximation of definite integrals. This is it right here. Basically, the error-bound for trapezoidal rule. If suppose k is a number greater than or equal to the absolute value of the second derivative for this interval where x is between a and b, and this, then basically what we have is the error of the trapezoidal rule, or the absolute value of the error, is less than or equal to k times b minus a cubed divided by 12 times n squared, where basically n are is just the number, the number of sub-intervals, and k is any number greater than or equal to the second derivative. Oh, the absolute value of the second derivative. Yeah, write that down, absolute value of the second derivative, and basically the lower the number, the more accurate the error bound, because you could just plug in infinity to k and you're just gonna it's still gonna hold true, just saying the error is less than infinity, which is obvious. So in proving this, let's just recall the basics of a trapezoidal rule. So if we recall what it looks like, we have a graph of, let's say, a function like this. This is x, y. Let's say we have like this. This is at, let's call this x0. A equals to x0 is the initial one. And this is all the way to b equals to xn, where we just basically break these up into n intervals or n sub-intervals of equal distance like this, and they're all trapezoid. So you just draw a line from each of these like that, like that, like that, and basically the distance between these two, this is, well, delta x, and this equals 2 if we were to say for any given one. This is, let's say, xi. This is xi plus 1. So what we get is this is just a difference, xi plus 1 minus xi. And again, this is just equal to the, well, these are all the exact same. So these are all delta x. So that if they're all delta x, this is just an average of the whole thing. So b minus a over the number of intervals n. So that's what we have right here. And also, like I showed in my earlier video, the summation of this using the approximation, we get, well, from a to b of f of x dx. This is roughly equal to the trapezoid approximation, which I went over, and this equals to delta x divided by 2, and then from summation from, this is all the way up to n, I equals to 1. Of now the addition of f of x I minus 1 plus f of x I right here. And you can see my earlier video on the trapezoidal rule to see how I got this. And this is basically the average of the left and right hand approximation. Yeah, now basically the error of using this trapezoidal rule is shown below, and what I mean by that is just where it appears in the equation. So if you have, this is the exact one we're trying to guess, from a to b of f of x dx. So now this equals to, let's say if we're using this approximation, equals t of n plus, well, an error, plus e of t. So this is how this this is the exact, so this equals to whatever this is, this t of n, the trapezoidal rule approximation, plus the error. And the error is basically the difference between these two to get the exact answer. Yeah, so now let's look at a single interval of this. So if we were taking, let's just say, this part right here, and just zoom in and just make it look really big so we can have a better idea. So we have, let's say, the function looks something like this, and this is at, we'll call this xi, and this is at xi plus 1. So this is right here. And now if we were to draw the trapezoid, what we have is, well, something that looks like this. I'll just write this all the way across, and there is our trapezoid. Now the height of this one right here is, well, f of xi plus 1. And the height over here is f of xi. And also this distance right here, this is our delta x, and this equals to xi plus 1 minus xi. And now we'll just call it h just to make it easier in the proof. So now the area of this trapezoid, I'll go a of t equals 2, well, this is, if you look at it, this could be considered, well, as an area of a rectangle plus a triangle. So that could be equal to, I'll just write it like this, draw it out. So it equals to this area, which equals to, yeah, so I'll write this better actually, like this, which equals to, well, this rectangle plus the triangle. Plus that, so this equals to, well, the area of the rectangle, that's just f of x I times it by h, which is our delta x. And now we have to add this area of the triangle, which is, well, the difference between these two is just, well, f of x I plus 1 minus f of x I, which equals 2, and then also multiplied by the base and then divide by 2. So this equals 2f of x I plus 1 minus f of x I divided by 2 and multiplied by the base. So base times height divided by 2. Just simple area of a triangle. So that's what we have. And just expanding this out, we get equals 2 f of x times h, and then this is plus h over 2 f of x I plus 1 minus h over 2 f of x I. And now what we could do is we'll subtract from these like terms of xi. This is then subtract by this. The same thing as writing 2 over 2. This is just becomes, well, same thing, 1 over 2. So this equals 2. Let's write it 2 over 2 here. What we get here is, and then take it out, h over 2 times it by f of xi plus f of xi plus 1. Right here, and notice this is exactly the same thing as over here, the summation that we have here, delta x, the same thing as h, and this is the summation of these two intervals, or the endpoints, and then divide by 2. So again, that's the exact same thing that we just did, but this is just for each sub-interval. So now to find the exact area underneath, that's just going to be the integral from xi to xi plus 1 of f of x dx, because again this function here is our f of x. Yeah, so now what I'm going to do is just change this variable to get rid of this xi. To do that, I'm going to do let, well, t equals to x minus xi. And the reason for this, well, when you plug in xi, that becomes 0. When you plug in xi plus 1, that becomes, well, our delta x, or h. So I'll explain that in a bit. So the derivative of this is equal to dx right there, and then and also if we, let's just rearrange this. So when you rearrange these two, we have x equals 2, move this over, t plus xi. So now at t equals to xi, we have, well, yeah, and now when we have at, well, x is equal to xi, this becomes, well, t equals to 0. And at x equals to xi plus 1, this is for these upper bound and lower bound, t equals to xi plus 1 minus xi, which equals to our delta x, or our h. So we could write this as equaling 2 integral from 0 to h of f of t, which is x now there, plus xi. And then dt right here, they just equal to it like that. And now basically if we integrate by parts twice, or the integration, yeah, the method by part, integration by parts twice, we will be able to get an integral containing f double prime of x, because that's what we are trying to prove here. So basically trying to write the summation in terms of, well, having this double prime of x, or the second derivative. So if we do that, what we get is basically, in this case, since we're using by parts, okay, now what we're going to do is let u, in this case, because we know, I'll just write this by parts, we have u dv equals 2, this is ab, uv, like just to recap on it, ab minus integral from ab of v now, dv. So that's the integration by parts, just a quick recap. So in this case, what we're going to do is let u equals 2 ft plus x I, and the reason for this is because the derivative, well, that's just going to be f prime dt plus x I. And now, because we have this derivative, and we do it twice, we're going to have a second derivative. So now, the next part is we let dv equals 2, well, dt. And now the integral of this is going to be equal to, well, this is an interesting part, t, and we're going to add a constant 1. I'll explain this later. Yeah, basically I'll explain why this is possible in a later video, because, well, this is just adding a constant called c1, and the reason we even can do this is because, well, the integral of dt, you always have to add a random constant, because when you take the derivative, we get, well, dv equals to dt plus this constant goes to 0. So we can actually do this at any case. I'll explain this in greater detail in my actually next video. And I'll explain why we're doing this in a bit soon. So we'll start to make sense why we're adding this constant, because in all my other integration by parts, I never add this constant. We never needed to, but in this one, this is pretty useful to add it there. So what we get now is the integral from 0 to h of f of t plus xi dt is equal to, and now our u is going to be, well, this, and then our v is that, so I'll put this in front, c1, and now we have f of t plus xi, and then this is from 0 to h, minus now the integral from 0 to h of, now our v is t plus c1, constant 1, I'll just write this there, this is constant, or integration constant. And now we add our u, which is our du, which is f prime of t plus x1, xi, I mean. Okay, dt. And now we do integration by parts again. So by parts, again, because we want to make this into the other way, into having a second derivative. So as you can see here, we have just regular one, so we want to get a second derivative in this integral. So what we get is, again, u is going to be, in this case, let u equal to f prime of t plus xi, so that du is equal to f double prime t plus xi. And then our dv now is going to be equal to these two again, t plus c1 times it by dt. And now the derivative here, the integral right here is going to be, well, equal to t squared over 2 plus c1t, and I'm going to add another constant again. This is a very useful thing. Actually, instead of calling it 2, I'll call it a star. The reason we're calling it star is I'm just going to rearrange this to get a better constant, a more neat and tidy one, and we can do that by completing the square here. So first I'll multiply by 2 on this, here's top and bottom, so this equals 2 t squared plus 2c1t divided by 2, and then plus c star. So now completing the square, I'll write this over here, complete the square. And when we do that, basically, because when we complete the square here, I'll write this as, because as you see, this is a 2c1t, we could have it written as 2 plus t plus c1 squared, and then this is going to be, well, we have to subtract a c1 squared, because what we have here is, I'll write it here, t plus c1 squared equals to t squared plus 2c1 when you multiply these all out, and then last one you need to multiply this by itself when you expand it, c1 squared. See what we've done there? So in order for this we need to subtract this c1, so subtract from here, and that's why I included this part here, so we're not changing anything. Then plus c1 star, and again, as you see, that's just a constant. So this would equal to t plus c1 squared over 2, subtract that out, c1 squared over 2 plus c star, and now this whole thing, I will set it equal to c2. So now we have a better constant. This is more neat and tidy. So t plus c1 squared, and then this is going to be now, plus c2, where c2 equals to c star minus c1 squared right there. So now that we've done all this, we can go ahead and plug these inside. So what we get, I'll move this all the way down. Move this all the way down right here. So we get the integral from 0 to h of f of t plus xi, is dt is equal to, so we write the first term right here, that's what it equals to, which is basically t plus c1 times by f of t plus xi, and this is from 0 to h. Then we have to subtract. Now our new uv is going to be equal to, put this in a bracket like this, uv is going to be f prime, and then our v is, this right here. So we're going to have this in front, c1 squared. This is a pretty ingenious proof right here. That's why I'm doing all these seemingly very creative topics right there. Concepts right there. So now we have this, and then times it by the first derivative, t plus xi, and then summation from 0 to h. And then we subtract. Now to get rid of these, just make it neater, I'll take this out, and I'll put a plus here, because the whole thing we were subtracting anyways, and now inside the by parts we have to, by parts there's a negative sign. So we'll make this a positive and make this a negative. Now we go integral from 0 to h of, actually I'll move it down here to make it have some room. So plus integral from 0 to h of now this part here, which is our new v, c1 squared divided by 2 plus c2 times by the second derivative t plus xi, and then we have it now, so now dt. And now the interesting part as well, let's choose c1 and c2, these two constants, such that we have the integral equal to the trapezoidal rule approximation plus an error. So just having two terms. And note once again, we can choose c1 and c2 to be any number because they simply cancel out when working out or expanding the integral. And also, stay tuned for my next videos. I will explain this in this very interesting aspect of integration by parts method. I'll explain in detail. So when we choose it to be anything we want, the idea is, we want this part to equal the tn, and also we want this part here, because in our because our approximation just has this, there's no derivative anywhere there, so we want this going to 0. So the first part we want, we want this right here, t plus c1 times it by f of t plus xi from 0 to h. We want it equaling to our this part right here. Where is it? We want it equal to this approximation. So we want it equal to, so I'll write that again. We want this to be h over 2 times it by f of x I plus 1. I'll just do this. Plus f of x I plus 1. Yeah, so if we want this, then let's just expand this out. So we plug in this h inside, we get h plus c1 times by f of, well, h plus xi, and again, this is just equal to xi plus 1. That's just delta x to the h, so that's just the second bound, and then we subtract, plug in the 0, c1 times by f of xi, like that. And now this has to equal to this side, to the right side, expand this out, f of x I plus h over 2, f of x I plus 1. So, now we have this, now we have to set this equal to it, and well, as you can see from here, if we let, well, c1 equal to negative h over 2, this part right here remains h over 2, so h minus h over 2 equals h over 2. Now there's an f of xi plus 1. And now here, because we're doing a negative, this becomes, well, this with this negative equals to, well, plus h over 2, which is exactly this. So there is our value. So c1 is equal to negative h over 2, because that makes this whole thing, it makes this, the first term, the trapezoidal approximation. And now, like I stated earlier, now we want to minimize the error by trying to set the constant c2 such that terms containing the first derivative f prime cancel out. This means that the error will be entirely just the integral part, so that's what we want. So we want to set this equaling to 0 and find a proper c2 value. So let's write this down. So, yeah, I'll write this down. We want this, what is this right here, t plus c1 squared over 2 minus plus c2, and then this is going to be, multiplied by f prime of t plus xi from 0 to h. So we want this all to equal to 0, so we don't need to deal with it. So now to do that, let's just first expand. So what we get, plug in the h, so we get right here h plus c1 squared divided by 2 plus c2 times it by this f of, well, this is plug in the h, that becomes h plus xi, and then we, well, subtract, plug in the 0, we get a, what we get right here is c1, I'll put this bracket, c1, actually I'll plug in the value because we know that, well, c1 is over here, so let's just plug that in. So I'll remove this, this is going to be minus h over 2, that's what we get. So here we get a negative h over 2 as a c1 squared divided by 2, and then plus c2, and then we have an f prime of, now this is going to be just xi. So we wanted this equal to 0, and the only way possible in this case is if both these terms equal to 0, but notice basically that these are the same. So this equals to this, and that's because, well, when you subtract this, that's going to be positive h over 2 squared. That's just going to be, well, when you square, it doesn't matter what's inside, it's going to be squared. So these are exactly the same thing. So I could write that down. So this means that this positive h over 2, when we subtract, squared over 2 plus c2 has to equal to 0, because these are the exact same thing. So to do that, that's the only way we can make all these terms equal 0 at all times, because these values are always changing. This f prime of, the derivative always changes based on whichever interval you're in. So we don't know what that value is, so we have to set these equal to 0. So as you can see here, when you expand this out, we get c2 is equal to, move this over, negative, there's an h squared, there is a, this is going to be 4 times 2, which equals to negative h squared over 8. So that's the value we have, and we just set c2 equaling to it. So if we set it equal to it, so if c2 equals this and c1 equals negative h over 2, what we get overall is the derivative from 0 to h, or just any interval like this, of f of t plus xi dt is equal to, and now we have, this is going to be our h over 2, and then we put this in bracket, f of xi plus f of xi plus 1. And then we have to plus our error now. Now the error is completely within our integral right here, which is, let's just go back up. So we've canceled this equal to 0, that equals to tn, or I'll call it actually ti, so that's for each ith one, and now we have this last part with the second derivative. So I'll write this down. I'll write this down with our new c values. So writing it down, where was that again? This is t plus c1, then plus c2. Okay. So we get t plus c1, which is negative h over 2 squared divided by 2. Then we have a minus h squared over 8. Now f double prime of x plus, t plus xi dt. So that is our integral right here. So this could be considered as our error. So that was our error, and this again can be considered as our approximation, because this is exactly what the trapezoidal approximation is. So t, I'll call it t of I, so for the subinterval. And I'll call this error here e, I'll call this et of, well, I. So this is a trapezoidal error, but for the ith interval. So what this means is, the total error right here is going to be equal to, it was when you keep summing these up, equals to e of, I'll just write this, equals e of t, which equals to, well, e of, there's an I, so let's call it the first one, so et 0, and then we add et right here, 1 plus etc., keep going on and on until we have the last one, et n minus 1. And the reason we have n minus 1 is because of our naming, what's it called? Our naming methodology we had when we looked at the interval. Scrolling back up, we went from xi to xi plus 1. So when we have the last interval n minus 1, we get, well, n minus 1 plus 1, we get to n. So when we go back to here, so there's an x0 and there's an xn right there. So that's why we go to up to here, n minus 1. So when you plug in this, you get x n minus 1 plus 1. That's what we are naming. Our naming methods, that's what we did. So this equals to, well, xn. These negative 1 and 1 cancel out. So that's why, that just explains why we have up to n minus 1. So this means now when we sum up this error, so for the first one, this is for I equals 0, so that's what we have. So when we plug this in, this equals to integral from 0, this is t minus h over 8 squared over 2 minus h over, actually no, this isn't 8, this is a 2. And then f of, now we have t plus x0 dt. Now we keep adding these up until, remember there's n subintervals all the way until we get up to, well, here, integral from 0 to h of t minus h over 2 squared divided by 2 minus h squared over 8. Now we have f double prime t plus, well, the last one, x n minus 1. And then we add, well, our dt right here. So now if you notice from this this summation right here, these are all the same. This part's the same. The only thing that's actually changing is this this part right here, this xi, is x goes from x0 all the way to xn minus 1. So that's the only thing changing. So using our basic summation or integral properties, we could sum these up into just something a bit neater. So this equals to the integral from 0 to h, and plug this all into here, t minus h over 2 divided by 2, write this bigger like that, minus h squared over 8. Now we have right here is a little summation right here, f double prime, no, and then we add the first one, x0 plus, etc. Keep going on and on until we get plus the last one, ft plus x and minus 1 dt. I'll write this like that. So we just made it a bit neater, write it in one integral. Now in the area-bound formula, we suppose that k is greater than or equal to the absolute value of the second derivative for this interval. Thus we can basically simplify this above summation by using this k value. First thing we'll do is look at the absolute value of this whole thing. So this equals to absolute value of 0 to h of, now we write this all out, t minus h squared, h over 2 squared minus h over 8. So put this in a bracket like that, and then this is times it by this whole thing here. So this is just a tedious proof video. Just then multiply like this, t plus x and minus 1, and then this is dt like that. So the absolute value of this whole thing, and now if we put this absolute value inside, this would be less than equal to, because the inside the integral could change from negative, positive, etc. So what we'll do right here is it will put this negative, put this less than or equal to sign, so we don't mess up anything around. Yeah, because when we put in now, I'll put this inside, put this negative sign inside. Yeah, I'll put this like this, t minus h over 2, and then this is squared. So when we put this absolute value inside, we are basically possibly changing the value, so we have to put this less than equal to sign. So yeah, because some of these might be negatives, when we put this inside, we're just forcing everything to be positive. So this would be, possibly bigger than the other ones. And also now I'm going to put the absolute value side inside every one of these. And then basically we use this to say that, well, this is probably bigger. So we're making everything positive. Now we'll have put this right here, t plus x is 0, absolute value, etc. And then like this, t plus x and minus 1, absolute value, and then dt. Yeah, so these are all absolute values, and now again there are n of these, there's n of these intervals like this, and now what we're going to do is something, basically utilize the fact that we're supposing k is greater than equal to this. So again, this would equal to less than equal to, and this whole thing's going to be less than equal to when we take out, assuming the maximum k on all of these, and taking it out, we get n times this k. So n, let's go n, yeah, so basically this is less than equal to n k, and this is a constant, so we put this out here, n k. Now integral of from 0 to h of absolute value of t minus h squared, like this, minus h over 8 over 2 dt. And now we just need to solve for this one. And notice this inside function right here. Notice it's a parabola. So let's let f of t equals 2, I'll call it g of t to be different from ours, equals to t minus h over 2 squared over 2 minus h over 8. So if we were to graph this out, this would be something like, well, first of all, at t is equal to, when you plug in, we'll add t equals 0 or h. Notice what happens. What we get is, well, we get negative, alright, g of 0 equals to negative h over 2 squared divided by 2 minus h squared over 8. And again, this would be equal to, this would be equal to h squared over 4 times 2 minus h squared over 8, which equals to 0. And same thing for t. We'll just have a positive h over 2. This equals to 0. I mean, not t, h. Oh yeah, so that also equals to 0. And notice when you graph it out, this is just a parabola. So this is t, this is g, and again, this is just a parabola. Since it's positive here, it's going upwards, and this is where we start off at the bottom, and to the right is plus h over 2. And you can see more on how to graph this in my earlier videos on graphing. So this is going to be our h over 2. This is our h. This is our 0. And again, this part right here is negative h squared over 8. Let's draw it like this. So this is exactly where we go off here, and it's going up and up. So it's a parabola. Yeah, so it's just a parabola going up like this. So what this means is that in this interval it's less than 0. So basically this is g of t is, well, it's negative less than equal to 0 for, well, t is less than equal to h greater than equal to 0. So equals to this. So yeah, since it's negative, what this becomes is, well, this just means that the integral of integral of g over t dt, this just equals to, well, negative integral of gt dt. And then when we plug this inside, this is our g of t, we just flip these around. So yeah, just flip these around left to right. So what we get is, well, integral from 0 to h, I'll put this here, 0h, 0h, this is going to be h squared over 8 minus, this is t minus h over 2 squared over 2 like that, dt. Now we just need to solve this out, and when we solve it, we get right here, this is a constant, so that just becomes h over 2t minus, again, t minus h over 2. It's going to be a 3. Put the 3 down, we get a 6 right here. This is from 0 to h. Plug these inside, we get an h cubed over 8 minus, put the h in here, we just get an h over 2 cubed divided by 6 minus, when we plug in this 0, we get right here, this cancels, we'll have a negative sign, and then this is a cubed, so we put in the 0, this negative one's going to matter, 3, because this goes to 0 divided by 6. Alright, so now if we expand this out, just simplify it, this is 8, this is going to be h over 2 cubed, which is 8, so that's 8 times 6. I'll just leave it like that. And now these negatives cancel, but there's a negative right here because it's cubed, it's still negative, so we put a negative right there. Now we have an h, 3, this is going to be 2 cubed, which is 2 times 2, 2 times 2 times 2, which is 8, put an 8 times 6, times by common denominator, top and bottom, 6, so we have everything divided by 8 and 6, we get, and then we just simplify 6 minus, well, 1 minus 1, 2, h cubed, 6 times 8 equals 2, 4 divided by 6 times, I'll just split this up, 2 times 4, h cubed, which equals to, these 4's cancel, h cubed over 12. So that's what that is. So now we can plug this back inside our integral right here for the error. So we get the error, this becomes, well, h cubed divided by 12. So let's bring it all back down. We get et, absolute value, is less than equal to nk, and we put h cubed over 12. And remember, h is just b minus a, so this equals 2 nk, this is b minus, actually this is b minus a divided by n, that's what h equals to, divided by 12, because h is just our delta x. And now, what we get right here, simplify this ends, what we'll get is equals 2 nk b minus a cubed divided by 12n cubed. Put this here, take these out, and write a 2 there. The n's will cancel, one of them will cancel. So that's what this equals to, but I'll move this down, write this better, less than, equal to, and there you go. That is exactly our proof of it. And now some important notes on this proof. Well, our derivation of the error bound lets us see some weaknesses in it. And one of the weaknesses is, well, the value of f double prime of x can vary from interval to interval. So this means that some values are actually much lower than the k value which we imposed on it, which was an upper bound. And also some values may be negative and some positive, so there can be cancellation among these terms. This means that the sum may be much less than the estimate as well. So both these ones lower what our estimate is. This one might be a bit too high. Thus, the actual value of the error is more closely related to an average value. Instead of saying imposing an absolute maximum one, we can go for an average one. Let's call m, and often it is often a negative value and smaller than the error bound estimate. So it's usually ET is usually equal to negative m times, well, b minus a squared, in fact. Yeah, and divided by 12, and right there. Yeah, and squared. So yeah, this is a more accurate guess of the error, but again, this sometimes we'll have it, well, opposite of what we have. This might be less than what the error we guess. So this is better for, well, saying an absolute maximum, so we don't go above this error whenever you're checking values of error values that you're willing to have for whatever particular application. And also, even though the average changes, so this m value changes as we change n, it won't change very much from one large value of n to another. So this is a more accurate version. Notice this squared as opposed to cubed, which again just lowers it based on these these weaknesses of the derivation we have. But again, derivation is for an absolute max, and this is the answer right there. Anyways, that's all for today. Hopefully you learned from this pretty extensive proof video. Hopefully you were able to follow along for quite a while. Anyways, like always, get down these exact notes in the link below, and stay tuned for another Math Easy.